we can continue from here, and I hope you can hear me. I could not complete few slides last time, so I will continue from there. Okay, so we were discussing about tuples. So suppose we have a set of n symbols, and the question is how many different sequences of length k we can form out of these symbols. Okay, so we can apply the argument as before. We can apply the product rule. Okay, so there are n possibilities to pick the first letter. Similarly, there are n possibilities to pick the second letter, and so on. Okay, so in this case, the number of different sequences of length k we can form out of these n symbols is n to the k, right? That's what we discussed last time. So we have a sequence of length k, and we have n possibilities, right? So n symbols are there. So I have n for the here, I have n for here, like I have multiple of this, so that's why I still have n. Okay, so even if I have used one symbol here, I have plenty of that. Okay, so I still can choose with repetitions. I can still choose the same one here. So this I always have this n. Okay, so in total, so by product rule, we will have n times n, which is, and this is k times. So this is n to the k. Okay. Okay. So let us move on. Okay, so we can apply this to some practical problem. Let us say a number of number plates. So consider some number plate format in India, which could be like this. Okay, so first one denotes the state, and then the following two-digit number stands for the district number, and then the following two letter is an RTO series. So this is like RTO, okay, for the transport office has some code, and then we have last four digits, and this is the vehicle number from within this range. Okay, so these are four-digit numbers. Okay. So the question is how many vehicles number plates you can generate, okay, given that you have these things, right? So we can apply the product rule, right? So this is a tuple of this many length, right? So this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is a tuple of length 10, but here the possibilities you have are, these are the letters, right? So you have possibilities you have are like 26. Here also you have like 26. Okay, I mean, we are assuming that we have all possible states here, right? So but we know that, okay, there are limited states in India, right? But if we think of how many tuples we can generate, allowing that we have all possible freedom, then but you could have restricted this, right? So because the states are like limited in India. Okay, so 25 or 26 are there. I don't remember exactly. So we can restrict that, but here we have the freedom to have choose. Again, like the point is like how many we have in practice. We have like fixed number of codes, or the districts are fixed. So it will be some limited number. Okay, so if we really want to compute this concretely, and then CP is also the RTO series, so this is also fixed. So those many, let us say this is like let us say M, N, P, many of them, and then here you have all the possibilities, right? So here you have like starting from 0 to 9. So let us say you have 10 times 10 times 10 times 10. Okay, so these many number plates will be there. Okay. Tuples with restrictions. So here we will see an example where we can combine sum and product rule. So let us see how many integer numbers are there between 0 and and 9999, right? So that have exactly one 5-digit. Okay, that have exactly one 5-digit. Okay, so how will you solve this problem, right? How many integer numbers are there between 0 and then 9999? Okay, that have exactly one 5-digit. Okay, so it's exactly, so these are tuples, but now you have put some restrictions, right? So now you are not asking for all possible. Now you are asking for things like this, exactly one. So this is the restriction we are talking about. Okay, so how we go about solving such problem, right? Okay, so let us see the numbers between the first observation is that the numbers between 0 and 9999 are sequences of digits of length 4. Okay, so the 3-digit numbers, the 3-digital numbers will correspond to sequences starting with 0. So if there is a 3-digit number like 459, okay, then we have 0 here in the front. Okay, so 3-digit number will be seen as a 4-digit number prepended by 0, right? Okay, we can place the unique 5 at any of the 4 positions. We can place 5 at any of the 4 positions, right? So we have 4 positions because this is a 4-digit numbers, and we can place 5 anywhere, right? So we can place 5 here, okay, and or we can place 5 here, okay. So we can place anywhere. So we have like 4 places where 5 can go, right? Okay, so this gives us 4 cases, okay, for the 4 cases where 5 can be put. If we compute the number of sequences in all 4 cases, we can get the answer by the rule of sum. Okay, so this is the plan we have, right? So there are 4 cases, right? So the first case is like I put, so this is a 4-digit number, I put, let's say 5 in the first place, and here in the remaining ones I have no restrictions here, right? Only restriction is that I don't have to pick 5 for these, right? So remaining places, what I'm left with are like 9. Okay, so remaining places what I'm left with is, sorry, so okay, so this will be like 9. Okay, and because for the remaining ones repetitions are allowed, okay, so 9 9, right? So another case would be we put 5 at the second place, and then here we have other places possibilities we have are 999. Okay, and these differ because they differ in the place of the 5, right? Okay, and then we have other cases, right? So 9 9 5. So 5 is like a, I'm not saying 5, so this is just a placeholder here, right? So is the location of the 5, but what we are changing, what we are observing in the remaining places are the number of ways we can put a number. Okay, and then sorry, it was 3, and then we have 4, so we have 9 9 9, and then 5 we locate it here. Okay, so these are the possible cases, right? So these are the numbers which have exactly 1 5. Okay, so these are the places we have which have 5 at exactly 1 locations, and in other places we have those options. So we know the answer to this now, right? So so we are combining 2 things here. We have sum rule and we have product rule first, and then we fix the 5 in one place, and then remaining places we have 999, and we are talking about the tuples here. So we have the product rule here. So it will be 9 times 9 times 9. Okay, possibilities for this case, right? And then similarly we have 9 times 9 times 9 possibilities for the second case, 9 times 9 times 9 possibilities for the third case, and similarly for the fourth case. Okay, and then they don't have anything in common, right? So these are the objects of type A, these are the objects of type B, and these are the objects of type C, and these are the objects of type D. So the sum rule says that one of these types, okay, will be the sum of these because they don't intersect. So the total will be the sum of these, right? So this will be the sum of these, right? Okay. Okay. Oh, okay. Let's see what I have written here. Okay, so I am doing a mistake here. Okay, so this will be like 9 times 9 times 9. Okay, if we fix 5 in one place, okay, if we fix 5 in one place, then the remaining places we have 999. Okay, it's wrong here. Okay, there's a typo here. And then we have four of these, right? So we have 4 of these. So we have 9 to the 3. So 4 times 9 to the 3. Okay. So you get the idea, right? Okay. Now let us. So now we can define permutations. Permutation are a special case of are special tuples, right? Permutations are special tuples in the sense that you have these are tuples with restrictions, and the restriction is that none of the entries in the sequence must be common, right? Previous case we said that only one place we have. I mean, only one digit will be 5. Okay? Exactly one digit will be 5, right? And remainings can differ. In permutations, you are saying that all the digits are unique. Okay, so that's the difference. So the tuples of length k, that's how it's defined, without repetitions are called k permutations, right? Tuples of length k without repetitions are k permutations. Okay, so let us see some examples. Suppose we have a set of n symbols. Okay, how many different sequences of length k we can form out of these symbols if we are not allowed to use the same symbol twice? So that's the permutation question here, right? Okay. So, but here we do assume that k is less than equal to n. Okay. So let us see. So we have what we are asking for is the k permutations, right? And n is greater than equal to k. So how many different sequences of length k we can form out of these symbols if we are not allowed to use the same symbol twice? That's what this is saying, right? Okay, so I have n symbols in hand and I have to fill k places, right? So okay, I was just checking the I was just checking your chat in case like someone had something. Okay, I believe it so far it's okay. Okay. Okay, so I come back. So this is permutation again. Like these are basic stuff. So we have k places to fill, and we have n symbols in hand. Okay, n is greater than equal to k. Okay, we will see that case where n can be less than k, but okay, we will see that again. But let us assume that k is less than equal to n. So first place, I have all the freedom in the world to choose any of the n. So that's why I have n. And once I have taken one of them out of the n, I'm left with n minus 1 to choose from, because I'm not allowed to use the same symbol twice. So once I have used a symbol in the first place, I cannot use it at all in any other remaining k minus 1 places. Okay, so that's why I am left with n minus 1 symbols. And similarly, in the third case, since I have used 2 symbols, now I'm left with n minus 2 symbols. So I have all the freedom to choose from the remaining n minus 2 symbols and so on, right? So this is how we do up to k, and this will be how much? N minus k minus 1, right? N minus k minus 1, right? So so by the product rule now we have so what are the all possible K permutations, right? So all possible K permutations, we just multiply by the product rule, n minus 1 times n minus 2 times dot 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 dot, and then n minus k plus 1, n minus k plus 1, right? Okay. So this is the K permutation formula that we have, right? So this is what I have written here, exactly what I have written here, and this can be written like this. Okay, this is nothing but the same thing, right? Because this is, because if you yeah, if you compute this out, it will become this, because this n factorial, n minus 1 and so on, and then we have n minus k, and then n minus k minus 1, and so on. So all those will get cancelled from here, obviously. Okay, get cancelled, and you get back this. Okay, so let us see some permutation examples. Okay, in how many ways we can arrange n different books in n different bins on the shelf. Now, important thing to note here is that the bins can take only one book, right? So, and there are n different books. So the scenario right now is that we have n different bins. Okay, n different bins. So these are the bins, and one bin can take only one book, right? So what are the possibilities? In the first bin, I have possibility to choose any of the n, right? So I have n possibilities. Here in the second bin, I have, since I have put one book in the first bin, now I'm left with n minus 1, n minus 2, and so on. Okay, in the end, I have 1 here. Well, this is a special case. So in this case, we have n factorial. Okay, n factorial ways. Okay, easy stuff. So this is just a special case of the previous case where we put k equal to n. Okay, so this was about permutation, and this is something I could not finish in the last class. Now I will go to, I will open the second slide. Okay, so I will now, I'm now going to open second lecture slide. Okay, so just to hold on a bit. And not this one. Okay. To close this, otherwise yeah, the PDF viewer is a bit yeah, it's it doesn't take my, okay, let me open. Yeah, this PDF viewer is a bit strange because it doesn't let me open. It's very strange. It does not let me open the another file just like that. So what I have to do is that I have to share it again. Let me share it again. Okay, so I'm back with the. Well, okay, let me. Strange. Stop sharing. Okay, so I stop sharing, and then I go back to these are annoying. Okay. Okay, so yeah, this PDF viewer is a little bit strange for me because it just I cannot do file open. I mean, this is very strange. It froze. Okay, so let us start with lecture 2 now. So lecture 2 we will discuss combinations and a little bit about Pascal's triangle. Okay, so let us see with an example. Combinations. You are organizing a car journey. Let us say you have 5 friends. But there are only 3 vacant places in your car. What is the number of ways of taking 3 of your 5 friends to the journey? Okay, so the most of you will say immediately, what is the answer? Okay, so and another way to reformulate this problem is what is the number of ways of choosing 3 elements out of a set containing 5 elements? Okay, so we know by now, right? So n choose k form, right? So these are the ways we find combinations. Okay, so there are 5 choices for the first friend. Okay, so we are now going to solve this. 4 choices for the second friend and 3 choices for the third friend, right? So now the question is how many choices are there? How many ways are there for choosing 3 friends? Assuming that ordering matters to you. So let us say ordering matters to you. So let us say we have Rajesh, okay, Mahesh, Ganesh, let us say Sita, Geeta. Okay, so there are 5 friends you have, and you want to choose 3 of them, and for you the ordering matters. So for example, let us say you choose Rajesh first, and then Mahesh, and then Ganesh. Okay, and this is different than choosing Mahesh, Rajesh, and Ganesh. Okay, so what you are saying here is like the way you are picking up, you distinguish between them. Okay, although the friends that you chose are the same set of friend, but the first one that you had a preference here, right? So first you chose Rajesh, Mahesh, Ganesh. The second possibility is like first you chose Mahesh, then Rajesh, then Ganesh. So let us assume that ordering matters to you. So then in that case, what are the ways you can choose the friend? Well, from the previous thing that we have seen, right? So that's permutation basically, right? Since ordering is matters to you, because right. So for the first place, you had 5 friends that you can choose, 5 possibilities. Then once you have chosen one, then you are left with 4, and then you are left with 3. Okay. So if you multiply them out, it's 60 choices, assuming ordering. Okay. And remember, in the original question, we didn't worry about ordering. Okay, the combination does not take into account ordering. Combination says that regardless of whichever way you pick your friend, okay, I don't care, but just tell me how many different sets of 3, size 3, right? So friends of group 3 you can pick. So for you, Mahesh, Suresh or Ganesh is same thing as Suresh, Mahesh or Ganesh. So permutation doesn't matter, right? But we start with permutation. Assume that ordering matters to you. Okay. So, but what we notice is that with each of the group that you have selected, because since you have assumed the ordering, you have counted you have counted a group of 3 friends 3 factorial times, right? Because Mahesh, Suresh, and Ganesh, you could have picked them in the 3 factorial ways, right? Because the permutation of this will be like 3 factorial, right? So you could have done this S, M, G or G, M, S. So all permutations of this, right? So in picking the 3 friends, since you did not distinguish until now, okay, you have counted, you have 3 factorial of them of the permutation of the three of them, right? So so that is a group of A, B, C is counted both as 3 factorial times. So we need to divide by the 3 factorial to get rid of these duplicates. This factor, right? So there's a 3 factorial factor that you have in your counting that has to be now divided by, okay? So that you get a unique group, right? It's unique in the sense like up to permutation, right? So, okay. So since ordering does not matter, we call them combinations. Okay, that's the difference between permutation and combinations. Okay, permutation ordering matters. K permutation is the tuples where the ordering matters, and then these are the tuples where ordering doesn't matter. Okay, that's the difference between. Okay, so we will formally define combination in the next slide. So this is the next slide. Okay, for a set S, a K combination is a subset of S of size K. Okay, so the thing about ordering doesn't matter is encoded in this subset notation, because in the set ordering doesn't matter, right? So you pick a set of size K. That's it, because in a set we don't care about ordering. Remember, in the definition of set we said ordering doesn't matter. So simply we can define it's a subset of size K. That's it. Now we define K combinations, right? So this is one combination. One K combination is a subset of size K. Okay, and then we can talk about how many of those are there, right? So then we talk about numbers, right? So number of K combinations with an S here, right? So then we talk about how many of these are there, because we are talking about counting problem here, and counting is related to computing probability. Okay, the discrete probability a lot matters on counting. That's why we are doing counting. Okay. So the number of K combinations of n element set will be denoted by this. This is a notation you may have seen before. Okay, it's called n choose K. Okay, that's how it's called, n choose K. And so this is the, for the moment you can take this as a notation, right? I have not defined, I have not maybe let us say derived it yet, right? I mean, in the example before we have derived it already. In the 5 friends, you are picking 3 out of 5 friends, you are picking 3 friends, right? So that that was essentially the proof. We can extend that proof here, right? Out of n friends, we want K friends, right? So we will go by the same logic as before. So n times n minus 1 times dot 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 n minus K plus 1. So that will be the K permutation first we will compute. And since in the K permutations, okay, so the proof of this is evident from our previous derivation of the example itself, right? So the first step is compute K permutation. So K permutation will be n times n minus 1 times, okay, so n minus K plus 1, okay. And since we cared about ordering in permutation, but combination says you should not care about ordering. So then we have to divide by the, since we are picking this K group of friends, and we cared about ordering, so those many we have to factor out. Okay, so that's why we divide by K factorial, right? So here itself you have the I mean, okay, sorry. Okay, so I don't mean like this is the same thing. Okay, this is not the same thing. What this is K permutation so far. Okay, and we have not defined this yet. Okay, this is K combination. Okay, and what this we have listed out is K permutation. Okay, so first step is clear. We know how to derive K permutation, right? And what is our goal is to derive okay, I think I'm mixing too many things here. Okay, so what is here is K permutation. Okay, sorry about. So what is here is K permutation, and what is completely this guy is actually combination, because then we have divided by the K factorial, right? Okay, so this is what we have, right? Okay, so the number of K combinations of an n element set is given by this. So what we have is n K. Okay, and sorry, this is like my Okay, yeah, here. Okay, so this is what we have. Okay, so the number of k combinations of an n element set will be given by this. Now let us derive this now. Okay, so let us derive this with an example here. So with an example here, how we can derive this, right? We have yeah, sorry.
Sir, can you check the chat once?
Okay, so let me check the chat. Um, okay. Yeah, what is like? Should I go faster? You are saying? Yeah, I
Sir,
can go
like
faster. I can go
if
faster.
we
Yeah.
go, we'll miss the stuff that we
Yeah.
actually don't have any idea about.
Yeah. Okay. Okay. I take that into account. Yeah, you know these things, but I'm just thinking that nothing should be left out. That's the problem. Okay. So we know this. Okay. And then quickly about Pascal's triangle. Okay. There are some examples where Pascal's triangle will be useful. So let me do it rather quickly. Okay. Um, the question is there are n students, and then what are the ways of forming k students out of them, and choose k. Done. Okay. This is the result that you may know again. Okay. So how do you prove this, right? So n choose k is n minus 1 choose k minus 1, and then n minus 1 choose k. Okay. So how do you prove this, right? Proof will follow in the sense like you pick a fix one element here, right? Okay, so you fix one element, and then you start counting. Okay, so for example, let's say one of the student is Ramesh, right? And then there will be a group with Ramesh included, and there will be a group with Ramesh not included, right? So the teams with Ramesh and teams without Ramesh, and then you apply the sum rule. Okay, so if you apply the sum rule, then you get the answer. Okay, and then you apply the sum rule, and then you get the answer that you need. Okay. Okay, done. So, and then we can apply this recursively, right? Because this is like a recursion here. So you can keep recursively applying the formula, because again this can be written like as you have done for nk. You can also break it up. You can also break this guy up. So essentially, what you have is a recursion for n choose k. Okay, done. So it's evident. Okay, I'm going a little bit faster as you have. Okay, so Pascal's triangle. I hope the sync is good, because last time I did a Google search, and then they said that GPU acceleration, if you have, then there is a lag. I hope I have turned off the GPU acceleration, and I'm hoping that today there is no lag. Okay, if there is still lag, we will try to fix that. Okay. Okay. So this is Pascal's triangle again. It's so the question is like, do you know how you grow the Pascal's triangle? Okay, so it's just a fun thing, but you can immediately recognize even if you don't remember. Okay, you can grow this very easily, right? So if I have to add another row, it's very easy. Okay, so how we do this? Like, okay, so we sum it like this, right? So we sum like this, we sum like this. So this way we can keep growing the Pascal's triangle. On the boundary, you can assume to be 0. Okay, on the boundary you can assume it to be 0, and then you can grow Pascal's triangle and so on. Okay, so it's easy stuff. But Pascal's triangles is related to few other things. There are many things here I have listed, but I don't have to like go into too much of the detail of that. Only some interesting things we can see. For example, at the second, if you go diagonally, second row it's counting number. If you go third row, it's a triangular number, and so on. Okay, so triangular numbers are like the number of dots in this triangle. So how do I grow these triangular numbers? Well, I add one more row with one more point. That's the thing. So I add one more, okay, and then one more, and then I just do this. Okay, so this way I get this, and similarly I add one more rows, and then join the last point, and then I make this. So the total number of dots that you keep getting, that is called triangular numbers. Okay, okay, done. So you can get the triangular numbers. What this says is that you can get the triangular numbers like that. Okay. What are the horizontal sums and exponents? So horizontally, what does it represent, right? So you have one here, you have two here. It turns out that the horizontal sum of this Pascal's triangle are nothing but the digits of the sum is 2 to the I. Okay, sum is 2 to the I. That is clear. Okay, so this 2 to the 0, 2 to the 1, 2 to the 2, and so on. And what about the actual entries here? They turned out to be the digits of the 11th power. Okay, 11 to the 0 is just 1. 11 to the 1 is 1, 1. So that you put 1, 1 in the second row. 11 to the 2 is 1, 2, 1. You put that in the second row, third row, and so on. Okay, so these are some observations for the Pascal triangle. There is a symmetry in the Pascal triangle. Okay, so I'm in the next slide. I hope the sync is good. So I'm in the so if we look at the symmetry, then from the symmetry we can arrive at this result, which is n choose k is n choose n minus k factorial, which is also evident, for example, here in the proof. Okay, I hope you are in the sync. So n choose k is n factorial by k factorial n minus k factorial, and then we have n factorial by n minus k factorial. So because we can just flip these guys, and then we have n minus k factorial and k factorial, so on. Okay. Yeah, so the sum of the numbers in the nth row of the Pascal's triangle is equal to 2 to the n, right? So that is something we have verified from the Pascal's triangle, but this is the formula that we have, right? So to prove this, it's to prove this recurrence, what do we do? It's like saying, so the first entry, if you see, it's like saying it's like picking subset of length 0, right? And then the second term is saying subsets of length 1. Okay, subsets of length n minus 1 and subsets of length n. So this is like saying number of subsets of a set, number of subsets of a set of length n. Okay, of length n. Okay, so this is something we also relate there, right? So which is nothing but 2 to the n, right? So these are the observations we have. I'm going to skip this a bit, okay, so that yeah, you are familiar with this anyway. So another result is like alternating sum is 0, okay, and that is also coming from the Pascal's triangle. If you, I mean, this is a example, okay, from here you see that, but a concrete way to prove would be odd size subsets are same as the even. Number of odd size subsets will be the same as number of even size subsets. So once you have this, you can prove this. Okay. Okay, so let us continue. So what is the number of 5 hand cards dealt of a standard 52 card deck? N choose k, done. Okay, so 52 choose 5. Okay, so you know this, right? So you're asking me to speed up, so I'm going to speed up. Count. Okay, what is the 5 card hands with 2 hearts and 3 spades? Okay, so how will you solve this? Okay, 5 hand cards where 2 of the cards are supposed to be hearts. So for this is an example. Okay, so let us say 2 of them are hearts. Okay, so this is the heart shape. If you have not played a card game, then don't worry. Okay, so these are called hearts. This is the red one. Okay, and then these are called spades. Okay, hearts and spades. So the question is asking, what is the number of 5 hand cards you will have with 2 hearts and 3 spades? Okay, what will you do? Okay, so you go and ask what is the number of ways of picking 2 hearts from 13 hearts, right? Because there are 13 hearts. Okay, 52 cards are there, and then 52 cards are there, and then 13 there are four different types are there, like hearts, spades, and so on. Okay, so you are talking about picking 2 2 hearts from 13 spades. So 2 hearts from 13, 2 hearts from 13 hearts, and 3 spades from 13 spades. Okay, so what will be the answer? So again, you will apply the product rule, right? So it's like 13 choose 2 times 13 choose 3, right? Should be the answer. Now apply the product rule. So 13 times 2, oh, I made a mistake here, right? 13 times 2 and 13 times 13 choose 3. Okay. So I hope this answer is still correct. Okay, I may have done a typo here. Okay. Okay, let us see another problem. What is the number of non-negative integers with at most 4 digits, at least one of which is equal to 7? Okay, so think about this. How will you solve this? These problems are now getting a little bit more tricky now. Okay, so what we are talking about is 4-digit numbers, and at least one. Okay, I'm not saying exactly one, right? So I'm talking about at least one digit is equal to 7. So how do you solve this? Right, so think about this. How do you solve about these things, right? Okay, so let's look into the answer. Okay, so the total number of 4-digit numbers is how many? 10 to the 4. Okay, that's now total number of 4-digit numbers that does not contain 7. That does not contain 7 would be how many? 9 to the 4. Okay, so there are 4 places, and since 7 is deleted from our list of 10 digits, so we are left with 9999, which is 9 to the 4. Okay. Okay, so what we have counted is 4-digit number that does not contain 7. So this two will give us the answer. Okay, so because now the number of 4 digits with at least one of the digit equal to 7 will be total number minus the total number of 4 digits that does not contain 7. Right. So these are the tricks you have to be familiar with to solve problems like this. Right. Now these are exactly the numbers that have at least one of the digit is equal to 7. Okay, we are saying at least one, right? Okay, so let us make it a little bit more tricky. Okay, so what is the number of non-negative integers with at most 4 digits? Now we are talking about at most 4 digit. We are not saying 4-digit numbers. We are saying at most 4-digit number. It could be, yeah, it could be like 1-digit number. It could be like 2-digit number, 3-digit number, 4-digit number. Okay, and whose digits are increasing. Okay, so let us look into this. So the digits must be increasing also, right? So we can choose 4 different digits, and we can arrange them in increasing order. Okay, that's something we can do. So now the thing is, ordering matters in the result, but the way we are picking, we can always order it in increasing order. Okay, so we can pick the 4-digit number randomly, not in increasing order, but we can rearrange them in the increasing order. Okay, we can rearrange it in increasing order, right? Okay, hence it is nothing but picking 4 different digits out of the 10 digits, right? And remember, it's going into combination form, right? Because I can always pick in any order, whatever, and then I can rearrange this. So I can, so it's more like a combination here, right? Okay, so this is why it's n choose k form, right? So 10, 4. So I can choose 4 out of 10. Okay, and one from chess. Okay, so one from chess. Let us see. A piece can move 1 step up or 1 step to the right. What is the number of ways of getting from cell 00 to the cell 53? Okay, so this is the cell 53. and this is the cell 0, 0, right? So what are the number of ways? Okay, now we are talking about number of ways. We are not talking about the moves needed, right? In the previous sum rule example, we talked about number of moves, but that will be useful here. Okay, but what we are talking about is number of ways we can go. So one way is like I can go like this. One way is like I can go like this. Okay, so you have to count all this move, right? Okay, so how do you solve this problem? Like what is n? In this case, the question you should ask is what is n and what is k? It's a combination problem, but what is n and what is k? What choose what, right? I mean, so this is something we have to figure out. So we want to go to the cell 5, 3, and the question is how many ways we can go. So to go to cell 5, 3, it involves 3 moves to the right and 5 moves up. Okay, so 3 moves to the right and 5 moves up. So total number of moves you have to take is 8, right? So the answer would be so the answer would be 8 choose 3. Why is the answer 8 choose 3? Okay, you are supposed to go to the cell 5, 3, right? You are supposed to go to the cell 5, 3, and you are starting from 0, 0, right? So the total number of moves that you have to do is 8, right? The total number of moves you are supposed to do is 8, right? So why do you think it's 8 choose 3? Can you explain, one of you? Remember that you have to you have like 3 ways, 3 moves you have here, right? But why should it be 3 here? Hmm. 8 places. We will choose 3 places to the right, remaining for the up. So it is this. Okay, I got your answer. It's correct. Yeah, chat seems to be a good thing, because otherwise talking, because sometimes audio and all this may not be correct, right? Okay, good. So you got it. And look, another possibility one could have asked is like, why are you like considering this? Why not this? Right? I mean, then the answer will be different. No, answer is not different, right? Because 8, 3 is the same as saying what? 8, 5. You can check. Okay, 8, 5 is same as 8, 3, right? This is why we studied the symmetry property, right? You could have also come up with this. Why should I say 8, 3? Why not 8, 5? Yeah, you can say 8, 5 also. It's the same thing. Numerically, they are same, right? Okay. Okay, so the answer to the previous problem can also be found using Pascal's triangle. Well, Pascal triangle is a fun thing. So you can just fill the Pascal triangle from the bottom, and then you grow the Pascal triangle. Like I said, the way to grow is like you add things like this, right? Okay, and then you reach the place wherever 5, 3 was there, right? So wherever 5, 3, maybe it was here. So whatever number you get in the Pascal triangle, that's the answer you have. Okay. So what we have so far, so what we know so far, okay, so this is like the summary part of the combinations and permutations, right? So let us see this table and recall this. So let us say we have k is 2 and n is 3. Okay, I think there is a typo here. Okay, so k is 2 and n is 3. So how many ways we can? What are the number of possibilities, right? when ordering is considered and we have repetitions. So when repetition is allowed and ordering is considered. So repetition is allowed here. So A and A, there was repetition, right? So B and B was there, C and C was there. So if you consider those with repetitions, then this many possibilities are there, right? If we do without repetitions, then it reduces to this. Okay, then we have removed this guy, this guy, this guy, and then we are left with this without repetitions. But these are still with ordering. So ordering matters here, right? Because this is ordering matters. Now, if we remove the ordering, then it further reduces to this, right? Because AB is same as BA, okay, and so on. And then if we do unordering with repetitions, right? So that's a special case we have not seen yet. Unordering with repetitions, then we have this, right? So let us look into recap the formulas, right? So far what we know is this. Ordering with repetitions n to the k. Ordering without repetitions is nothing but k permutations, and this is this. And then we have unordering without repetition is this. This is the part that is left to fill, okay? And that I think I will take 1 minute or 2 minutes more, okay? I'm not sure if I can complete this now, okay? But let me do as much as possible. So this is something that is not yet filled, okay? But it can be derived with some simple tricks, okay? So is there any formula for this, right? So that's what we want to see. We have not seen this yet. Well, the problem is to do this, we need, I need a little bit more. I need a little bit more time. As you can see, I have like 6-7 slides left for only this part. So let me do this in the next class.